Good afternoon, my name is Fabio Gonzalez, and I'll be presenting the Chapter 9 overview alongside my partner Donovan. So we're going to go ahead and start by distinguishing between systems and surroundings. So a system refers to the part, interaction, or object of interest, while a surrounding is all of the external environment that surrounds the system. And there's three types of systems: closed system, isolated system, and open system. In an open system, energy and matter can be exchanged between the system and the surroundings openly. In a closed system, only energy can be exchanged between the system and the surroundings. And then an isolated system, neither matter nor energy can be exchanged between the system and the surroundings. Let's go ahead and look at some examples and distinguish between systems and surroundings. So let's go ahead and say we're looking at a pan with water on a stove. So the system would be the boiling water in the pan, since what's of interest is the boiling water evaporating. So that means that the surrounding would be the air around the pan, the stove, as well as the pan walls. So let's go ahead and look at a second scenario. So let's say we're doing a calorimeter experiment. So the system would be the combustion reaction happening, while the surroundings would be the calorimeter walls, parts, as well as the water. Moving on to exothermic and endothermic processes. An exothermic process is a process that releases energy, whereas an endothermic process is one that takes in energy. And this energy is usually thermal energy in the form of heat. So let's go ahead and look at some examples. So let's say what type of processes occur when bonds form or break. So which type of processes would these be? So when a bond forms, that would be an exothermic process, since when bonds form, they release energy, and this involves releasing energy to the surroundings. And then when the bond breaks, that's always going to take in energy, since the atoms want to be bonded. So this is going to be an endothermic process, since it's going to have to take in energy from the surrounding in order to break that bond. Alright, so now let's go ahead and look at the relationship between changes in enthalpy and heat flow and work. So when the change in energy is negative, the process is exothermic, since energy is being lost to the surrounding, which explains the negative sign. So this means that heat has to be flowing out of the system for the change in internal energy to be negative. And this also means that the system is doing work on the surrounding, and then since it's releasing its energy to the surrounding. And then when the change in internal energy is positive, this means that the process is endothermic, because energy is being gained. And then this also means that heat is flowing from the surrounding into the system, since that's the only way that energy can be being added into the system, and thereby making it endothermic. This also means that the surrounding is therefore doing work on the system.
Now we will be discussing how to calculate changes in energy and using calorimetry data to calculate enthalpy. So first, let's talk about heating curves. Heating curves allow us to see changes in temperature and changes in physical state of a substance. As you can see in the bottom left, there is a graph that displays the relationship between energy input and temperature of a substance. From A to B, an input of energy results in the increase of temperature. However, as we approach a phase change from B to C, in this case a solid melting to a liquid, energy is required to break down the intramolecular forces that hold the substance, in order to result in a change of physical state. The same occurs as we go from a liquid to a gas. Generally, more energy input will be required to go from a liquid to a gas rather than from a solid to a liquid. This relationship also occurs when we work from the other way around, so from a gas to a liquid and from a liquid to a solid. The heating curve of a substance is also dependent on the heat capacity of that substance. Heating capacity is the amount of energy required to raise the temperature of a sample by 1 degree Celsius. However, more commonly used specific heat is energy required to raise 1 gram of substance by 1 degree Celsius. Specific heat is related to the energy transfer of a substance through the formula Q equals Sm delta of T, where Q is the energy, S is specific heat, M is mass, and delta T is the change in temperature. Now we will be talking about calorimetry. Calorimetry can be used to find the energy required by a substance to change its temperature. However, the formula above can also be used to find other variables, such as if you already had the energy inputted but needed to find the final temperature of a substance. For example, it asks how much energy is required to heat 50 grams of water from 20 degrees Celsius to 80 degrees Celsius. The specific heat capacity of water is 4.184 joules per gram Celsius. We would use the formula Q equals specific heat times mass times change in temperature. So we would have 4.184 joules per gram Celsius times 50 grams times 80 degrees Celsius minus 20 degrees Celsius. Grams and Celsius cancel, leaving joules, and we get 12,552 joules. That will sum up calculating changes in energy and calculating enthalpy using calorimetry data.
Let's go ahead and move on to finding the enthalpies of reaction using Hess's laws and average bond energies. So starting with Hess's laws, we're asked to give the enthalpy of reaction of methane. And remember that with Hess's laws, it tells us that we can add the several steps included that are needed for the formation of a product. So that's what we're going to go ahead and do. So we're given 3 equations as well as their enthalpies of formation. And each of these equations is going to give us one of the elements or molecules needed to complete our equation and find the enthalpy of formation of methane. So for our first one, the first one that's given to us, it gives us the molecule of hydrogen gas that we're going to need. The second one gives us the atom of carbon that we're going to need. And the third one gives us the molecule of methane that we're going to need. So we're going to have to go ahead and flip some of these around, and some of them we'll have to add coefficients in order to get our final equation. So as you can see, we're going to start by flipping the third equation. So it's going to give us carbon dioxide plus two molecules of water gives us a molecule of methane and 2 molecules of oxygen gas. And then we're going to go ahead and add the first equation to that, and we're going to go ahead and multiply the whole equation by 2. So we're going to add a coefficient of 2 to all the reactants and products, giving us two molecules of hydrogen gas plus 2 molecules of 1/2 oxygen gas gives us 2 molecules of water. And we go ahead and do this because we see that in our original equation we're going to need two molecules of hydrogen gas. Lastly, we add the carbon plus oxygen gas gives us carbon dioxide, and we can leave it as is because it gives us one atom of carbon, which we need as given in our original equation. And then also notice that since we had to flip the third equation that we used, the sign of the enthalpy formation of it is going to go from negative to positive. Since we're flipping the reaction, it's going to go from exothermic to endothermic. And then once we add all those up, we see that our final chemical equation is going to have some of the same reactants and products on both sides of the equation. So we go ahead and cancel those out. This is going to give us the original equation of 1 atom of carbon plus 2 molecules of hydrogen gas gives us a molecule of methane. And then we go ahead and add the respective enthalpies of formation of the equations we used. So we have 890.3 kilojoules per mole. And you can see we changed the sign from negative to positive since we flipped the equation. And then for the second equation we used, which was the one that included the molecule of hydrogen gas, we doubled the value of the enthalpy of formation because we have to double all the reactants and products. And we also add negative 393.5 for the third equation we used, which included the carbon atom. And this is going to give us an enthalpy formation for methane of negative 74.8. And all those individual enthalpies of formation were given to us, and we can add them up because of Hess's law. Another way of finding, or at least estimating, enthalpies of reaction is by using average bond energies. So let's go ahead and do this using an example. So we see we have nitrogen gas plus 2 molecules of oxygen gas gives us 2 molecules of nitrogen dioxide gas. Alright, so first we're going to have to see which bonds we're breaking and which bonds we're forming. So we're breaking a nitrogen gas triple bond, and we go ahead and search up the average bond energies. So for the nitrogen triple bond, we find that the bond energy is 945 kilojoules per mole. And then we're also breaking the oxygen double bonds, and we're breaking 2 oxygen double bonds since we have 2 molecules of oxygen gas. So we search it up and we see that we have that each of the bonds has a bond energy of 498 kilojoules per mole. So we're going to go ahead and multiply by 2 since we have 2 molecules of oxygen gas. And then we see that the bonds we're forming are a single bond between the nitrogen and oxygen and a double bond between the nitrogen and oxygen. And we have 2 molecules of nitrogen dioxide gas. So we're going to go ahead and multiply both of those by 2 and add them together, and this gives us a total bond energy of 1,616 kilojoules per mole. Right, so then to estimate the enthalpy of reaction, we go ahead and subtract the average bond energies of all the bonds that were formed from the average bond energies of all the bonds that were broken. So this is going to give us 1,941 minus 1,616 gives us 325 kilojoules per mole. And the reason we're subtracting the average bond energies of the ones formed is because to form bond energies it requires releasing energy. So those are exothermic reactions. And to break bonds, it's going to be an endothermic reaction. So to break a bond, you need to input energy into the system.
Now we'll be talking about the enthalpy of solution. So we have sodium chloride dissolving in water, and we want to find the enthalpy of the solution. We must consider that energy is required to break apart the ions in sodium chloride. This energy is known as the lattice energy, which in this case is positive 774 kilojoules per mole. Then we must consider that when sodium chloride is dissolved in water, the negatively charged regions of the water molecule will be attracted to the positive sodium ion, and the positive charged regions of the water molecule will be attracted to the negative chlorine ion. These are known as the ion dipole forces. So the energy of these ion dipole forces, or the heat of hydration, is negative 770 kilojoules per mole. If we want to find the enthalpy of solution for sodium chloride, we must find the difference between the lattice energy and the heat of hydration. So 774 kilojoules per mole minus 770 kilojoules per mole will leave us with positive 4 kilojoules per mole. So this will be an endothermic reaction. On to estimating lattice energy using the Born-Haber cycle. So as we stated before, the lattice energy is energy required to separate a mole of solid into a gas of ions. The enthalpy of solution is the enthalpy change when 1 mole of an ionic substance dissolves in water to give a solution of infinite dilution. We can use the Born-Haber cycle to estimate the strength of ionic bonds. It is generally difficult to do so directly, so we can find this by using Hess's law to find this indirectly. Hess's law allows us to find the change in energy by breaking the processes into various steps. For our example, we will be working with sodium chloride. First, we consider the enthalpy change from solid sodium to gaseous sodium, which is positive 108 kilojoules per mole. Then we have the dissociation of a diatomic chlorine into a singular chlorine, which is positive 122 kilojoules per mole. Next is the removal of an electron to form a sodium cation, which is positive 496 kilojoules per mole. This is also known as the first ionization energy. Then we have the addition of an electron to form a chlorine anion, otherwise known as the electron affinity, which is negative 349 kilojoules per mole. Now, using Hess's law, we can find the standard enthalpy of formation through the summation of enthalpies for all the steps. So our lattice energy would equal negative 788 kilojoules per mole. That will conclude estimating lattice energy using the Born-Haber cycle and Hess's law. Finally, we'll be discussing fuel value and density. So first off, fuel value is the amount of energy in a fuel by mass, whereas the fuel density is the mass of fuel per unit of volume. If we look at the graph in the bottom right from the reading, we can see that as hydrocarbons get longer, their fuel value decreases because of the ratio of carbon to hydrogen decreases. This means that more carbon dioxide is formed rather than water when it combusts. And because the formation of carbon dioxide releases less energy than water, it causes fuel value to decrease. In the graph, we can also see that density of fuel increases. This occurs because the fuel will weigh more if volume is kept constant. So we can use the ratio of carbon to hydrogen and fuel value to compare the various fuels and see which one may be better, such as in the table on the bottom left. Hydrogen has a higher fuel value than the other fuels, meaning that it releases more energy by mass. That will conclude our Chapter 10 overview. Thank you for listening.